I hear what you say about me. Mr. Brocious tells me.
What do you say about you?
Yeah.
We say all good things about you.
It's just the material that drives you nuts.
Yeah.
I'm giving you some new definitions here. Electronegativity. How do I want to say this?
What's up?
Propensity. Electronegativity. It's the propensity or the strength with which atoms, when they're involved in bonds, draw electrons toward themselves. Okay, so we'll wrap your mind around that in a second. Ionization energy. The energy needed to remove electrons from an atom. And finally, this is an easy one. Size. I don't think I really even have to define that. Just how big the atom is. And how does this relate to what we've been talking about in terms of our orbital diagrams and our ideas of principal quantum number? So these quantum numbers are going to determine something about size, and our electron configurations are going to determine something about ionization energy and electronegativity. Okay. So, first of all, let's tackle the easiest one first. If you take a look at the periodic table, I got to give this to Bryden, so I'm going to put the old periodic table this way. What's wrong? If you take a look at the periodic table, atoms obviously have different sizes. And if you remember when we were talking about these principal quantum levels, that n value, I want you to think about like an onion. If you've ever taken a cross section of an onion, when you have those concentric rings. Well, that's kind of like the atom. Take an atom, and I just have the n equal 1 principal quantum level. I'm only going to have that 1s orbital there. I jump down to the second row, and then I have my 2s orbital and the 2p orbitals. So I just want you to think about the s orbitals for a minute. So we have the 1s orbital, filling that up in the first hydrogen and helium, 2s orbital for lithium and beryllium, the 3s orbital comes next for the third period, 4s, 5s, etc. So if you had to make a prediction about size as we go down a column, what would you think about the size of the atoms? They get bigger, yeah. And that's a size trend. As we move down a column, the size gets larger because we're filling orbitals that are farther and farther away from the nucleus. Now, what happens if we go across? What do you think? Think it gets bigger? What? I'm not saying you're right or wrong, but what's your justification for that?
So we got capacity, we got 39.19, and all the way, right? You have 82. I mean, it keeps getting bigger.
Yes, but the atoms get smaller as we go across the periodic table. And I'll tell you why. Because it's what's going on here is as we move from left to right on the periodic table, sure, we're adding more electrons, But what else is happening in the nucleus? We have more what? Well, what do we have in the nucleus to begin with? Protons. Protons, neutrons. So if I go from like sodium, I have 11 protons, 11 electrons. I go over here, I've got 14 protons in the nucleus and 14 electrons. So what you're seeing is as we move from left to right, you have an increased nuclear charge. And that increased nuclear charge actually causes the electrons to be more attracted to the nucleus. So you actually see a little shrink of size as you go from left to right. It's counterintuitive, but that's what happens because, like, let's say I've got 14 protons here, so I have a positive 14 fundamental charge in the nucleus, 14 electrons, and so it's going to actually get a little bit smaller. We'll pull up some pictures of that as well. Yeah, so size, increase as we go down, decrease as we go across. Something else about size. Oh, these people who go on vacation in the middle of the year. I want to talk about sizes of ions versus the atom. If I've got sodium atom and a sodium ion and a chlorine atom and a chloride ion, you're going to see something interesting happen to the size of these things. The size of the parent atom, if I form a cation, I've got 11 protons in the nucleus. I take one away. How many electrons do I have left? 10, right? So those 10 electrons are going to feel that nuclear charge, and it's actually going to contract somewhat, quite a bit actually. So the cation is always going to be smaller than the parent atom. On the other side of the coin, if I have a chloride, I'm putting another electron in, giving it 18 electrons, 17 protons. It's going to expand because you have electron-electron repulsion. So the size of your anion is going to be bigger than the size of your parent atom. So that's something. Usually on a quiz or a test, I say, I list things. Which is larger? This is going to be potassium or potassium plus 1 or something like that. So just these are some loose ends we're just tying up.
So the plus is small.
Yeah. Because if I have 11 protons in the nucleus and 10 electrons, it's going to feel that more of a positive charge and kind of contract a little bit. Actually, quite a bit. So let's go back to some of these other ideas. Ionization energy, the energy it takes to remove an electron. Let me draw the orbital diagram here for a second for sodium. And my 1s, my 2s, my 2p, and my 3s orbitals. And it looks like that. And remember what I said about why sodium wants to get a plus 1 charge? Because it wants a full, what's that? Valence shell, yeah, it wants a full valence shell. So if it loses that electron, it's going to have a full valence shell. It's going to have that electron configuration of neon, actually, which is very, very stable. So it wants to give up that electron. So the energy it takes to remove that electron is not a lot. It takes a little bit of energy, but not as much as some other atoms. Let's say we go to the other side of the periodic table, and we look at chlorine. Let me see here. Yeah, we'll do chlorine. 1s, 2s, 2p, 3s, 3p, and then we'll start filling our electrons. 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, 1 in each before 2 in any. Now, let's think about this. I can have a full valence shell one of two ways. I can lose 7 electrons, or I can gain 1. It's a lot easier to gain 1, as we learned, to become a chloride ion. So chlorine doesn't want to lose electrons, it wants to gain electrons. So this is going to have a higher ionization. It's take more energy. If you tried to make this positively charged chloride, some chlorine cation, you're not going to do it. Ionization energy is just too high. So when we look at the periodic table, when we go from left to right, the ionization energy increases. So we go from left to right on the periodic table, IE increases. Does that kind of make sense to you why that's the case? All right, now let's look at the periodic table again. And I want to see if you can kind of relate what we were talking to about size to ionization energy. Let's say I'm looking at lithium and I go down to cesium. What do you think is going to happen with the ionization energy as we go from top to bottom? Remember, you're removing electrons. It's going to get smaller. It's going to take less energy to remove an electron from cesium.
Because they have more electrons.
Well, not only the fact that it's more electron, look where your outermost electron is. The n equals 6. Right here, our outermost electron is in the n equal 2 level, still feeling a lot of that nuclear charge. Down here, cesium, it's way out here in the n equals 6, 6s orbital, and I've got 54 electrons between that electron and the nucleus. So there's something called shielding that goes on. It doesn't feel the full nuclear charge as much as lithium. You only have 2 electrons between that outermost electron, and it's all real close too. So as we go down, ionization energy gets less, but as we go across, ionization energy gets higher. So that's something I think is important for you to realize. And this last thing, electronegativity. This is not going to really be that important right now, but next chapter, electronegativity becomes huge. And we're going to delve into that more in the next chapter. But what I want you to think about is if I have atoms involving covalent bonds, like let's say I have water. These atoms in a molecule have a different ability to pull electrons toward themselves. Oxygen really wants to pull electrons toward itself. And it goes back to this idea with the orbital diagrams. These like to become anions, the non-metals. But if they're involved in a molecule, they don't become anions. They just share electrons, but they share them unequally. So atoms with higher electronegativity will pull electrons toward themselves in a molecule, and the more these electrons are pulled toward this atom, this almost gets a negative charge to it. We write that little delta symbol. That's a Greek lowercase delta, and that's the minus charge. So that means that this has a partial minus charge. These guys down here, they get kind of like a partial positive charge. Not like a full-blown ion, but this is really interesting because it sets up in the molecule something called a dipole. A dipole means the molecule has one part of it that feels more positive, and the other part of it that feels more negative. We represent that by this sort of a cross and an arrow that goes through the molecule. Again, we are going to spend, next chapter is all about intermolecular forces of attraction. So I just wanted to introduce the topic of electronegativity, so when we get to the next chapter, you'll have heard the word. And I'm just going to tell you the trend really quickly. As we move across, electronegativity increases. As we go down, it decreases. So fluorine, for example, very tiny atom, really wants that electron, if it can get one, to be an ion, but if it's involved in a molecule, it'll pull electrons toward itself. Fluorine is the most electronegative element on the periodic table. But as we go down to like bromine and iodine, they're much less electronegative. Okay, so that is officially the end of this chapter, officially done. And I put the practice test up. You want to get out, check out, you have your phones with you, or a device? Purely for academic purposes.